Hi everyone. So today we'll be presenting narrowing the gap between serverless and in-state with storage functions. This presentation is given by me, Salaja, Divya, and Natch. So first up, we want to go through the authors and affiliations. There are 4 authors and they're all from the University of Utah. So starting off, we want to start with the motivation. So serverless computing, there's benefits and consequences. First, let's go through the benefits. It enables fine-grained resource provisioning, high-density multi-tenant resource sharing, and on-demand scalability through lightweight isolation techniques. This is really good because it drives up the utilization, and it also benefits the customers because now they're better fitting cost to resource use. So the benefits are really good here. However, on the other end, there's the consequences. And so one of the consequences is functions are stateless. Now, this is a really important problem that serverless computing has, and we'll go more into depth later in the presentation for it. And since it is stateless, it also forces functions to access all data remotely, which then externalizes all state into remote cloud storage. And so these are some of the consequences that serverless computing has. And so the main problem is that serverless functions are stateless. That is the main problem that we want to fix here. And so it is good in a way that it is stateless because it eases provisioning and fault tolerance. However, applications nowadays need access to data and state. It's just something that you need nowadays. And so because of this, there's this growing gap between cloud applications and their data. And serverless computing is just widening this gap. So we're trying to find a solution to better fix this. So nowadays, we use traditional cloud storage systems. And that's what we use today. And so the main idea of this is to ship data to code. And this works, but it's also very inefficient in moving data over the network. Why? Because of the low throughput and high latency. With the low throughput, we don't know if all the data is reaching its destination. High latency, it's just taking a really long time. And so as you can see in the graph, there's an optimal rate of latency and throughput that you want to reach, but with the traditional cloud storage systems that we have nowadays, we're at the end of that where we're at high latency and low throughput, which is not a good place we want to be at right now. And also with traditional cloud storage systems, it cannot offer fine-grained resource accounting and on-demand scalability. And so it also compromises the benefits of the serverless model, which is huge because if it's compromising the benefits, then what really are the benefits? So one of the existing solutions we have now is the fast ephemeral stores. And so this does solve the problem because it is designed to hold state between different functions. So it does solve the problem, however, it doesn't address the fundamental problem, which is the data shipping. Again, the shipping data to the code. And so because it does not compute data at its location of record, it provides limited data access models. And so one example of this is SQL. And companies that are emerging nowadays are finding it difficult to use SQL because if they just want something short and computationally intensive, then SQL is not the best way to go about it. They want something where you can get the data or you can you can compute where the data is. And so that's kind of a problem nowadays, and SQL is an existing solution, but also it's not working to its full extent right now. And so just to reiterate, the motivation here is that traditional cloud storage systems cannot offer the same level of fine-grained resource accounting and on-demand scalability, thus compromising the benefits of the serverless model. So if it is compromising it, then what exactly are the benefits here that we're working with? So we want to find a solution to this. And so one of the ideas that comes to mind is, instead of shipping the data to the code, why don't we flip it? Why don't we reverse the flow of data? This way, we can reverse the flow from computation to storage instead of the other way around. And why we want to do this? Because compute has a natural portability in the serverless design. So that means it's very easy to move code, whereas it's not that easy to move data. And so next we want to talk about the proposed solution that's mentioned in the article. So the proposed solution that's mentioned in this research paper is Shredder. And what is Shredder? It's a new cloud store designed for serverless function chains. And how it works is it embeds small storage functions within the store. And Shredder has 4 main key goals here. And so one of them is programmability. So with programmability, tenants should be able to embed arbitrary functions within storage, but they should also have very easy access to their data. So they should seamlessly be able to access their data even though it's within storage. So that's programmability. With isolation, we want to make sure that both the code and the storage of different tenants should be isolated. This just ensures data integrity, security, and just make sure your data is secure and no one's messing with it, basically. So you want to keep that data and code, like the code and the storage, isolated from different tenants. Then comes high density. So this is pretty high density and granularity. So this just means that Shredder should support thousands of tenant functions. So we don't want to do 100, like a few hundred. We want to do 1,000. We want it to be high density and it can be able to handle a lot. Last is performance. And so Shredder should make the raw performance of a storage server available to applications. And so that's kind of what we want to do with performance. So these are the 4 key goals that Shredder has. And so we'll talk more about the design in the next upcoming slides. But just to talk a little more about Shredder and what it is, in order to meet the performance goal, Shredder uses kernel bypass networking and a user-level TCP stack. And so again, we'll go more into this in the design part, but that is something to keep in mind as we go through the presentation. And also, for the performance goal, tenants route function invocation requests to storage server cores. And so this is also really important to keep in mind about Shredder. And lastly, just for some fun facts about Shredder, a single Shredder server can process more than 4 million function invocation requests per second, and it can also have less than 50 millisecond response times. So that's really good, and that's also a really good, it's just the performance goals and everything with the goals is a really good idea. And however, there are some newer applications out there. This is a good solution. It addresses a couple, like most of the problems that we have, and so next we'll go on to the design, and Divya will talk more about the layers, the kernel bypass, and more in Shredder and how it works.
The network layer and the function layer. The storage layer hosts all the tenants' data in memory and has a get and put key value interfaces, which is something we can think of hash map, which consistently gives big O of 1 performance. The network layer handles network connections, protocols, and requests of all tenants. If the incoming request is a simple get or put operation, it calls through storage layer. And if it includes a particular storage function, then network layer calls through the function layer. The function layer It highly relies on V8 runtime context. It matches incoming requests to storage function code and context. Now let's explore in depth about each layer in coming slides. Also, let's first look into the benefits of this three-layer design. We can map any resources to any tenant at any granularity, thus by achieving resource sharing. By separating storage from functions, the structure is avoiding coupling. It must also be able to fluidly map network resources across tenants. It maintains the performance of kernel bypass by managing thousands of tenants and giving each tenant its own hardware virtualized access to the network card. Shredder's separated network layer takes care of multiplexing the resources and hence by achieving the scalability. Now let's look in deep about the storage layer. All tenant records are allocated as single in-memory record heap. Different tenant records are intermixed at arbitrary granularities. No internal fragmentation between tenant storage. The storage layer keeps a hash table for each tenant that maps keys for its data records. To ensure performance, it is implemented in native code and exposes get and put functions. Now let's look into storage function layer. Storage function layer has one main important component called V8 runtime. The shredder fundamental design to achieve its low latency and high throughput is driven by V8 runtime. Each core in system gets its own V8 runtime and this runtime takes care of installing and running storage functions. The V8 runtime's just-in-time compiler internally translates functions into efficiency code and it also acts as a sandbox, preventing accessing one tenant's code to getting manipulated by other tenants' stored data. Context switching within V8 runtime is less expensive. Now let's look into the next slide, and here we are looking into how the storage function layer is interacting with the storage layer. Functions are expected to interact intensively with data and hence by adding significant overhead and limiting optimizations. As a result, each tenant context contains logic from the storage layer in an intermediate V8 representation, the CSAIR, which is nothing but cipher security algorithm, which is used to encrypting and decrypting purposes. The storage layer retains ownership of the physical resources that make up the records and indexes. But CSA code within the runtime is given read-only access to these structures. The CSA version of get directly looks up values in the hash tables in storage layer. By using the code generated from IR, tenants can effectively traverse the structures without execution, leaving V8 runtime. Henceforth, these functions enable shipping code to data. Now let's look into the network layer. It handles incoming packets, user level network protocol processing, RPC request framing, user level task scheduling, and request dispatch. Network layer functionality. It uses kernel bypass networking and each CPU core in Shredder polls for incoming network packets. This avoids the overhead of the Linux kernel, networking stack, system calls, interrupts, and scheduler interactions, and it gives Shredder high throughput, low latency, and fine grained control over request routing and scheduling. The network layer works together with tenants to spread load over cores to avoid centralized bottlenecks and spread load. Trust model. Tenants do not share state and cannot communicate through Shredder. Our only goal is to achieve tenant isolation. It should not be able to access to each other's state. Cannot store state without giving through its storage function facing interface. By achieving all these goals, we can conclude that Strider is a trustworthy model. Now let's look into the implementation. Strider is built on C star, runtime that combines kernel bypass through Intel's DPDK with a lightweight, event-driven asynchronous programming framework, built around a share and nothing philosophy, making it easy to scale across cores. Communications between cores happen through message passing. Isolation and context management. Strider must enforce isolation in record storage and tenant code. As we have earlier seen in storage layer, it just stores the functions and depending upon the tenant's access, it will give the particular tenant context for each tenant. Thus, it provides isolation. Relies on V8 context to isolate tenant provided code. Independent V8 instance is allocated for each core. Each isolate runs code from different tenant contexts one at a time.
So zero copy data access. And so what this is that storage functions use get and put calls to access records. And so they operate over the records through these remote get and put calls, which require moving them over the network. And so this optimizes the get and put because it avoids copying records into and out of storage whenever needed. So that's basically what the zero copy data access means. And so how it does this is Shutter allows the local get and put in storage functions to operate over records with no copying by implementing in-context array buffers in V8. And so this saves the round trips and data movement overhead. And so what array buffers are they allow Shutter to safely store pass-bounded views of memory. And so this is really efficient in how they're doing this. And because of that, code within a context can read arbitrary data from the buffer. So this is highly efficient, and it's one of the few reasons that about how the implementation is done in Shredder. This is why it's really good. And so, however, it is efficient, but some data-intensive operations suffer when control must be continuously transferred between context and trusted store code. And so eliminating the boundary crossings with CSA, this eliminates control transfer between tenant provided code and the store. And so it does this by simple read access records and enabling direct access to stores, metadatas, and indexes. And so that's a good way to kind of let all the consequences of zero copy access are getting resolved by this. And so it achieves this by implementing in-context store operations with the V8's CSA. And so how it does this, or how it works, is that, for example, Shredder takes input through the get call, then it would compute its hash, and then it indexes into bucket arrays, as you can see in the picture, and then it compares keys at allocation pointed to by bucket. And so as you can see in the table, this is how it works, and it is a good way of improving the zero copy access and the consequences of that. Next, we have the evaluation by Natch. So just before we go on to the evaluation of Shredder's application, just to reiterate what the design and implementation are. is the design was again 3 layers: the storage layer, the storage function layer, and the network layer. And each of these plays a very major part, a key part in Shredder's design. Each part has its own needs and its own way of making Shredder more efficient and easy to use, which is why Shredder handles the problem of serverless computing, which is the stateless problem. And so with Shredder, it is decreasing the gap between the cloud applications and their data. And it is really solving this problem. And so next we have the evaluation of Shredder's design and how Shredder has been working and what it can improve on, plus what it has improved already.
Experimental setup. The evaluation was carried out on a 3-node cluster consisting of one Shredder server and 2 clients. Both the clients and the server used a user-level TCP stack with kernel bypass networking. The evaluation explores Shredder's overhead compared to simple get and put operations. This calibrates how much work Shredder's programmability needs to make up for in order to improve efficiency relative to a typical key value store. The paper also explores a number of applications ranging from select protect join with aggregations functions, graph analytics, and machine learning use cases. Overheads and costs. Cost of isolation due to invoking operations through V8 adds overhead. As a result, when Shredder is running on 16 cores, the V8 isolation cost is much higher than when Shredder is running on 1 core due to poor V8 scalability. The researchers believe that with some engineering effort, it is possible to improve V8 scalability. Then the V8 isolation cost will be much cheaper. CPU scalability, measuring how the system scales. A micro benchmark is run to measure the CPU time spent performing a simple GET request for Shredder and no isolation. The, the result shown in graph B. The CPU time increase for no isolation is much less compared to Shredder when scaling from 1 core to 8 cores, and from 8 cores to 16 cores. This confirms that the poor scalability of V8 is the root cause of Shredder's low scalability. It is likely that V8's poor scalability can be improved. Tenant scalability. The experiment runs the server on 16 cores with the number of clients connections fixed at 1024 and varying the number of tenants on the server. The result shows that the number of tenants has almost no impact on no isolation approach. However, V8 approach adds a small overhead and the server scales well to more than 1000 tenants with about 6% performance decline. CPU time analysis. Analyze the amount of CPU time spent performing the GET request for each of the configurations. The result also shows that V8 overhead increases when Shredder scales to more cores due to the increase of V8 overhead. The benefits: minimizing data movement. In many cases, pushing code to the storage server can substantially reduce the data transferred over the network. A simple experiment is run in which clients issue requests to get a projection of multiple values stored on the server. Each stored value contains an array of 32-bit integers. The goal of each request is to get the first element in the array. With Shredder, the projection can be done on the network with storage function, which returns only the first element. Without Shredder, clients need to get the whole value from the server, which results in more data transferred over the network. Minimizing remote requests. Another benefit of pushing code to the storage is it reduces the number of remote requests a client has to make to perform an operation. The result is fewer network round trips and client stalls. An experiment is set on an application that traverses lists in the storage layer and returns the value at the end of each traversal. Without Shredder, the client has to iteratively read value from the database to find the key of the next node. Shredder performs significantly better as it eliminates data movement. This is the key to good performance. Impact of kernel bypass. Kernel bypass lowers network overhead. The configurations of each of the approaches that depend more heavily on request response are impacted the most by eliminating kernel bypass. As the graph shows, the results of running list traversal experiment without kernel bypass using traditional get and put operations suffers the most, since it needs to synchronously fetch every value traversed from the store. This shows that Shredder's storage functions are even more effective if network overheads are high. To evaluate Shredder with a more realistic workload, the researchers built a graph application on the Ego Facebook dataset from the Stanford Large Network Dataset Collection. It consists of friends list dataset. The dataset is stored as key value pairs where keys are IDs identifying a person, and the value is an array of IDs representing the friend list of that person. The application performs k-hop queries for randomly generated keys on the social graph. In one hop query operation, it fetches the friend list of a person. Then it gets the friend list of each friend and it sums up the length of the friend list. For the Shredder approach, all requests, including simple gets, are served through functions. Combined approach. The simple get requests are served directly by the database without entering V8. And the one-hop graph queries are served through the function in V8. The result shows that the combined approach improves the performance significantly. The higher percentage of simple GET requests in the workload, the more benefits from the combined approach. For AI and machine learning applications, databases are often used to serve trained models. Once trained, models must be deployed to a prediction serving system to provide low latency prediction system at scale. Shredder can be leveraged to push prediction functions to the database where models are stored. This is an advantage as models can be very large in size. A downside, a downside of this approach, because prediction code are compute intensive, shredder prediction functions must be implemented in JavaScript or WebAssembly. Both are slower than C++ native code. The question is, can the benefits of shredder outweigh its downside? A prediction service is set up on fully connected neural networks on the Iris dataset and Y dataset with a size of 76 bytes and 352 bytes, respectively. The inputs for the predictions are also stored in the database. For Shredder, the storage function gets the model and an input vector from the store, and then makes an inference. For remote approach, the get put operation fetch the neural network and the input and computes the inference at the client. For Iris dataset, with small models of 72 bytes, the remote get put approach achieves higher throughput than Shredder. This actually shows the case in which the benefits of Shredder cannot outweigh the disadvantage because inference is computed in C++ code at client, whereas on Shredder, inference is implemented as JavaScript storage function. However, for Y dataset, Shredder outperforms remote get put as the network bandwidth become bottlenecked on larger dataset. To conclude, even in cases of CPU-bound requests, Shredder can show more benefits than traditional remote get-put approach, as it entails a large amount of data transfer over the network. Moreover, Shredder has potential to achieve better throughput without requiring a specialized model serving service or customization at the storage layer. Conclusion: to ease scaling and fault tolerance and to drive high utilization results in the increasing gap between computation and data in applications in cloud storage systems. The paper presents Shredder. Although there is some downside to the approach, however, using storage functions, Shredder helps eliminate data movement overheads by bringing functions near the data they operate on. It helps eliminate data movement across the network, between the network card and storage functions, and between storage functions and data to achieve better performance over traditional remote approach. Thank you.
Thank you for your time listening to our presentation. If you have any questions regarding our presentation, narrowing the gap between serverless and its state with storage functions, please let us know down below in the Canvas page and we'll get to your questions. Thank you again for your time and have a good day.